Start to record. Guy, the floor is yours.
Thank you.
As they say.
As they say. Okay, so this is going to be kind of a continuation of Alex's talk from 2 weeks ago. So Alex talked about our works about an optimal inverse theorem over large fields for kind of an inverse theorem for tensors. So I'm going to make this talk, formally speaking, it's going to be self-contained, but the background part I'm going to go over very quickly. So do stop me if you have any questions, but my goal is to get into the more technical parts as quickly as I can. Okay, so what are the objects in question? Tensors. So here are the 3 facets of a K-tensor. You can think of a K-tensor as a K-linear polynomial, which is just a polynomial of degree 3 with individual degrees 1. So that means every monomial is of the form, xi times yj times zk, etc. So you have k sets of variables, and every monomial has one variable from each set. These are perhaps the nicest polynomials you can work with, and in a sense, every polynomial can be symmetrized to give a tensor. So there isn't much loss of generality in just talking about k-linear polynomials. Another facet, another way to think of tensors is just as an array of numbers. Namely, so these numbers are just the coefficients of the polynomials. Okay, just like in a two-dimensional tensor is just, you can think of it as a matrix of numbers, or you can think of it as a bilinear form. Alternatively, you can think of a two-tensor as just a linear map, right? That's basic linear algebra. And you can do the same if you have a 3-dimensional array of numbers, then just as you see in the drawing below, you can slice it along one of the axes, doesn't matter which for most questions. And you get a bunch of matrices, and each of them, of course, is a two-tensor. So each of them is a bilinear map. So again, every K-tensor corresponds to a map, certain k-1 linear map. Okay, so that's a tuple of polynomials of degree k-1 instead of k. So as an example, if you have for k equals 3, the identity 3 tensor as a polynomial, it looks like this: x1, y1, z1 plus x2, y2, z2 plus ... Visually, as an array of numbers, it's just an array of 3-dimensional array of all zeros except ones on the diagonal. And as a bilinear map, it just looks like that: x1, y1, that's the first component, x2, y2, second component, and so forth. Okay, what are the main stars of the play? So we have analytic rank and partition rank. Here's the definition of analytic rank. Intuitively, it measures the bias. If you think of the tensor as a function, then it measures the bias of this function. It's only defined over finite fields. So we're going to, for most of the talk, work with finite fields. This is the finite field of size q. So one way to define it is kind of a Fourier theoretic definition. So this was originally defined by Gauss and Wolf in the context of high order Fourier analysis. But we will stick with kind of the more concrete definition. If you just switch to talking about the corresponding map instead of the tensor, the corresponding k-1 linear map, then this is just the normalized, essentially it's the normalized number of zeros of these polynomials. Okay, so you have a bunch of polynomials, the components of the map, and you ask how many solutions do these polynomials have, joint solutions. So this notation, just to get the normalization right, so you take a uniformly random input to these polynomials, and you ask what's the probability that the output is going to be the 0 vector, so 0 in all the components. And if this is q to the -10, if this probability is q to the -10, then the analytic rank is 10. Okay, so this is the definition of analytic rank. In terms of the range where this quantity lives, it's a number between 0, not necessarily an integer, by the way, between 0 and n. This is y. Let me skip that. And of course, both extremes exist. So the analytic rank of the identity tensor is essentially n, and the analytic rank of the zero tensor is obviously 0, because then this probability is the probability that the corresponding map is 0 is obviously 1, so the analytic rank is 0. Okay, so Alex again talked about all of these things, so I'm skipping ahead. That's analytic rank, measure of bias. Next is partition rank, which intuitively is a measure of algebraic structure. So what are the most structured polynomials? Product polynomials, right? So if you have a tensor that can be written as a product of, look at this example, a polynomial on the x variables, or tensor on the x variables, and a tensor on the y and z variables, okay? These joint sets of variables, then these are essentially the simplest polynomials, and we call them partition rank 1 polynomials, or I should say partition rank 1 tensors, okay? And generally speaking, the partition rank of a tensor is just the minimal number of rank 1 tensors that sum up to give our tensor, okay? And this is a notion of structure because you express T as a whole as just a sum of a small number of very structured pieces, okay? So in terms of the range, partition rank is again a number between 0 and n. In this case, it is an integer. The lower bound is obvious. The upper bound is also kind of easy because you can, express your polynomial as maybe I choose the vertex set of the z variables, and then I have z1 times everything that multiplies that, plus the z2 times stuff, etc. So each of these summands is of partition rank 1, right? Because this is z1 is just a polynomial. It's a tensor it's actually a linear tensor in one of the variables set z, and this guy doesn't depend on the z variables. So the two variable sets in the two multiplicants here are disjoint, non-empty. Anyway, so you have here n summands. So you always have the trivial decomposition with n summands. Kind of a random, a generic tensor is going to have partition rank close to the maximum n. Just like, by the way, for analytic rank, a generic tensor is going to have analytic rank close to n. And you can look at the identity tensor, and it can be shown. It's not completely obvious, but it can be shown that it has maximal partition rank n. And of course, the partition rank of the zero tensor is 0. Okay. So we have this analytic rank and partition rank. Both of them are numbers between 0 and n. What's the relationship between them? That's a main question. That's kind of a basic question, right? If you can think of it as an extension of basic questions in linear algebra, but it's also very much related to fundamental concepts in additive combinatorics, for example, and it has other applications. So if you're talking about k equals 2, so we're talking about two tensors, aka matrices, aka linear maps, then these two quantities are the same. Analytic rank is equal to partition rank, which is not surprising given the fact that for matrices, there's really only one notion of rank, right? The notion of rank that we teach kids in the linear algebra course. So analytic rank and partition rank are both equal to that standard notion of rank. Okay, if you want to see the proof, here's the proof. You can talk about, let's look at the corresponding linear map to that two tensor. And then if we talk about computing the analytic rank, then this is what we care about, the probability that this linear map gives you the zero vector. But this is just, the normalized size of the kernel, right? We're talking about a finite field. So the kernel has some finite size divided by q to the n. Q is again the size of the field. But of course, the kernel is a linear space. So we know exactly how many points it has. What's the cardinality? It's the size of the field q to the power of the dimension of the kernel. Well, now use rank nullity. So you get q to the minus the dimension of the image. And as we teach in linear algebra, this is just equal to the rank. And we're done, right? Because then if this probability is q to the minus rank, the rank of the matrix T, or the rank of the linear map, then analytic rank is equal to that negative exponent. And then again, another theorem from linear algebra is that you can define the partition rank is just, if you're talking about matrices, this is just writing your matrix as a sum of rank 1 matrices, which again is equal to the usual notion of rank. So we're done. Partition rank and analytic rank both measure the same thing for matrices. What about order K tensors, 3-dimensional arrays, 4-dimensional arrays, etc.? Well, we always have the easy direction. It's always true that the analytic rank is at most the partition rank. So Alex mentioned that. Let me quickly go over the proof of that. So here it is. So suppose that T has a partition rank R, so you can decompose it as the sum of R summons, each of them of the form AI times BI, tensors in disjoint sets of variables, and there's no loss of generality in just assuming that the Z variables are used by the BIs, and so the AIs are independent of the Z variables. Okay, there's absolutely no loss of generality there. So this comes from our assumption that, if we have a tensor of partition rank R, then we have this decomposition of 40. On the other hand, if we want to talk about the analytic rank, then we should probably talk about the corresponding map, right? And the components of this map we know are just the derivatives with respect to one of the variable sets. So T1 is the derivative of T with respect to Z1, etc. Okay, so now let's tie those two things together. Notice that because we have this decomposition for T, this partition rank decomposition for T, then we have a nice decomposition for the derivatives of T, right? You take the derivative of T with respect to Z1, Z2, etc. Then you get this decomposition using the fact that the AIs are independent of Z. But this is interesting because you only have R AIs, but you can use them to express all of the N TJs, all of the components of the map. So in particular, if you have an input X that makes all the AIs equal to 0, okay, if you have a solution for just the AIs, then you also have a solution for all the TJs. Okay, that exactly follows from this decomposition. So if we want to talk about the partition, if you want to talk about analytic rank, then we're talking about the probability that the map equals 0, which is at least, now we know, the probability that this X is 0 of the AIs. But these are just R polynomials, and then you can show using basically linear algebra that this is because the AIs are multilinear polynomials themselves, and this is at least Q to the minus R. R is what we denoted the partition rank, so we're done, right? Because we showed that the analytic rank is now at most the partition rank. Okay, that was a bit quick, but again, Alex roughly went over this. Feel free to stop me with any questions. Okay. And the inverse conjecture says that the partition rank can be bounded from above by analytic rank times, and this is the more kind of the very optimistic conjecture, that times some constant, some quantity that depends only on K, which we usually think of K as a constant. This is kind of amazing, right? Because for this statement to be true, because it says that if your tensor is biased, so if your tensor has, kind of some number of zeros, then automatically that means that can be explained by a global structure so you can express T exactly as the sum of a few simple pieces, right? Partition rank 1 pieces. So this is a very surprising conjecture, right? Again, just because something about the number of zeros, you can immediately deduce something about the structure of the entire thing, the entire tensor. Green and Tau were the first to prove that something like this is true. So they showed that the partition rank can be bounded by some function of the analytic rank. Okay, so an inverse theorem is true, but then the question is what's the best dependency? And so, you can go over the proof of Gin and Tao, or or rather the refinements by Kaufman and Ovet and Bomik and Ovet, and then you will get Ackermann type bound. So an Ackermann type function is a function that goes much faster than a tower of exponentials. It's an iterated version of tower of exponentials, and it's actually much bigger than that. Anyway, so it's a qualitative bound, not a quantitative bound. Nevertheless, this has this already has qualitative applications, right? So it's, as I mentioned before, it's very much related to the inverse theorem for the Gauss norms. It has applications for some Nullstellensatz versions over finite fields. It has algorithmic applications in coding theory, etc., complexity theory. As I said, all of these applications inherit the horrible Ackermann type bounds from before. What else is known? So for very small values of k, when k is equals to 3 or 4, then some much better bounds are known. So Haramati and Shpilka proved the polynomial bound. Okay, so that's much more sensible. Partition rank is at most analytic rank to the 4th power. But this is only for 3 tensors. For 4 tensors, more recently, we also have a polynomial bound. But what happens for general k? This is a much more complicated question. I just mentioned that an even more recent progress, it's again a work with Alex and independently obtained by the Prasito, Koshdan, and Ziegler. So we were able to essentially settle the conjecture, the inverse conjecture, for again 3 tensors. So again, we were able to show that a partition rank is at most some constant times the analytic rank. So not a power, not like the 4th power of the analytic rank, but a constant times the analytic rank. That constant is maybe 8 or something. But the more interesting question is what happens for K-tensors. So there was this big breakthrough by Milichevich and Yenzer, who proved a polynomial upper bound for any k. And again, it's polynomial if you think of 2 to the 2 to the k squared, if you think of this as a constant, because k is a constant, that this is a polynomial bound. But that was the first time that something like this was shown, so that was a big deal. And the work with Alex, the more recent work with Alex, shows that, so we proved the conjecture in the sense that we have a constant. So the power of the analytic rank is 1, and there's just a multiplicative constant. The only caveat is that we assume that the finite field is somewhat large. So what do I mean here by somewhat large? I mean, it will be interesting to prove this for the binary field of size 2. That we don't know how to do. But the somewhat large here, it only depends, it's just some function of the analytic rank, which is actually, it actually makes it useful because, right, if the analytic rank of your tensor is large, then by the easy direction, we know that the partition rank is large. This is always true. This is easy. We proved that 2 minutes ago. So if the analytic rank is large, the partition rank is large, and there's nothing to prove. So really, kind of intuitively, the inverse question is only interesting if you know that the analytic rank, if you have some upper bound on the analytic rank, right? If the analytic rank is quote unquote small. But if you have a control over the analytic rank, then you also have a control over how large the field has to be. Okay, so the field doesn't have to be, if the analytic rank is somehow bounded in your application, then so is the size of the field that you need to work on. Another thing that I can mention is that if you go over our proof in detail, then you can see that the dependence here on the fields, so the field size has to be at least double exponential function of the analytic rank, but it's actually not that bad because if you can improve that to a single exponential, then you essentially get this result over any field, including the binary field, with the caveat that now the exponent of the analytic rank is not 1, but 1 plus little of 1. Anyway, let me not talk about that too much. The take-home message that at least if the field is somewhat large, then this partition rank notion, which is maybe easy to bound for explicit tensor, and the analytic rank, which is some quantity from higher order Fourier analysis, they both measure essentially the same thing. Okay, so let me pivot to the actual proof. Any questions, by the way, about the statement that we're proving? Okay. So proof strategy. So what we're going to do is we're going to use tools from kind of basic tools from algebraic geometry and the local analysis, by which I mean we look at tangent spaces, which is quite different than what Yenzer and Milicevic and others previously did in this line of work, which use certain results from additive combinatorics, and their analysis was more of a global nature. Okay, so maybe before I begin the proof, let me very quickly just flash a few slides of basic concepts in algebraic geometry. If you're very uncomfortable, if you're not comfortable with them now, you won't be after I flash those 2 slides. But let me just refresh the memory of those who have seen these concepts before. So I just kind of like, you can read this more slowly while I'm talking, but let me just highlight the most important definitions. So a variety is just the solution set of a bunch of polynomials over the algebraic closure. So when I'm talking about a solution to a polynomial or a zero of a polynomial, I mean that the coordinates are from the algebraic closure of our, say, finite field. Okay, so we start with a finite field. Its algebraic closure is a certain infinite field. And once we agree to talk about solutions in algebraic closure, then suddenly the tools of algebraic geometry are available to us. And we say that a variety is defined over the field F, or an F variety, if it's cut out by polynomials, if it's defined by polynomials with coefficients in F in the field. Okay. Another basic fact about varieties is that every variety can be written as the union of irreducible variety. And kind of that's a trivial statement, because the definition of an irreducible variety is just that you can't write the variety as a union of subvarieties, okay, of strict subvarieties. So this is always true that you have a variety. It's not necessarily kind of one irreducible thing, but it might have many irreducible components. All of them together are defined by this bunch of polynomials. Here's the formal definition of dimension, but the intuition is we can just stick with the intuition. Dimension 0 variety is just a finite set of points. A variety of dimension 1 is just a curve or a finite union of curves. Dimension 2, etc. Intuitively, it's kind of a measure of the degrees of freedom. The codimension is just the complementary term. So the number of variables minus the dimension. That's the codimension. And the last definition here is the definition of an F rational point, or an F point. So an F rational point is a point on your variety whose coordinates are all in the ground field F. Okay, so not from the trivially in the algebraic closure, but it's actually in the ground field. And we denote by V parentheses F, the set of all F rational points in the variety. Okay, so that was a bit much. If you've never seen this before, if you have, this is nothing new. So I'll just move on. Another definition, which is the tangent space of a variety at a particular point. I'm not going to go into the formal definition, but let's look at these examples. So on the left here, in orange, I have a curve with a variety of dimension 1. Okay, so this orange curve is defined by some polynomial in the variables x and y. And here is a black point. There is a particular point on this variety, and we can talk about its tangent space, this blue line. So the tangent space is always a linear space, or fine space if you shift it. So for most of the points, as you can see here, this is just a line. So it's the tangent space of dimension 1. For a generic point, for most of the points on the curve, the tangent space as the same dimension as the variety. But there are some special points, non-singular points, for example, the origin here, that for which the dimension of the tangent space is actually larger than the dimension of the variety. These are non-singular points. Okay, so it's always true that the dimension of the tangent is at least the dimension of the variety, but it can sometimes be strictly larger. Okay, so that's it for the terminology from algebraic geometry that I will need, or at least 80% of it. What about what we call total derivative? Another name for it is just the Jacobian. So let me remind you what's that. So first of all, what is a rational map? A rational map is just a tuple of rational functions. A rational function is just a ratio of two polynomials. Okay, so we will work a lot with rational maps. You can think of them as functions, except it's a misnomer, right? A rational function is not actually a function in that it's not defined when the denominator is 0, right? So this is why I'm using this dotted line to remind us that a rational map is not literally a map, not literally a function. It might not be defined everywhere. Okay, so if I have a certain rational map F, okay, just a tuple of rational functions, I can talk about its total derivative or its Jacobian. This is just the matrix of all partial derivatives of all functions. So again, I take any of the functions in this rational map, and I take the partial derivative with respect to each of the variables. Okay, so if I have m functions and n variables, I get an m by n matrix. Or you can think of it as the tensor product of the space Fm and Fn. I'm ignoring dual spaces for the sake of simplicity. Which, by the way, you can, once you have this Jacobian, this matrix, you can talk about the directional derivative with respect to a certain direction. You just multiply this matrix by your direction vector. Okay. So why do we call this total derivative instead of just the Jacobian? It's because we're going to iterate it. We're going to talk about a second derivative and third derivative, etc. Why can we do that? So notice that you can think of df, the Jacobian, is a matrix of, you can think of it as a matrix of polynomials, or a matrix of rational functions, matrix of functions. But a matrix, you can also think of it as a tuple, a very long tuple of functions, right? So it's again a rational map, and you can take its total derivative again. But now, so the first total derivative gave you a matrix. If you take another total derivative, then you get a three-dimensional array of functions. Okay? So we can talk about the order A total derivative. It's a rational tensor, okay, whose entries are just all the possible partial derivatives with respect to A of the variables, any multiset of the A variables. The thing to notice here is that if F to begin with was just a polynomial map, not even rational, just a polynomial map of degree 10, then if you take the total derivative 10 times or 11 times, then what you're going to get is a matrix, is a, I don't know, 10 or 11, whatever dimensional array of functions, but now each of the functions are going to be a constant. Okay, so the point is that every time you apply the total derivative, you increase your dimension, but you decrease the degree of the functions in the entries. Okay, and this is what we're going to do. So we're going to start with a tuple of low degree polynomials, take enough derivatives until we get just, well, a huge, a high dimensional array, but of numbers, and those numbers are essentially the coefficients of the original thing, the original map.
So you're not going to be working with rational, but with polynomial maps?
So both. What I said just now applies to polynomial maps. Yes.
Right,
but
because rational functions, you won't actually get a decrease in the degree.
Right. So it's going to be fun. We're going to, on the one hand, we're going to have a polynomial map that we're going to take derivatives of. But on the other hand, we're going to express it as a rational map. But this, this equality will only be defined at points where, the denominator is not 0. Okay, so you will see the details. But yeah, the last thing I said about the degree is decreasing, that applies only if we're talking about a polynomial map to begin with. So you have all the usual rules of derivatives, kind of just extended. Maybe the first one is the only non-trivial property. The chain rule looks a bit different now. But anyway, not very interesting. Okay, we can finally talk about the structure of the proof. So the proof has two parts. In the first part, we're going to work over the algebraic closure. So it's going to be all algebraic geometry. The second part is, mostly algebraic geometry. The second part also algebraic geometry, but there we're going to transition to the ground field. Anyway, part number one. So first we're going to talk about, so we're starting with our K-1 linear map. That's the object that we're starting with. We're going to take its Jacobian, or its total derivative. So this gives us a polynomial matrix of functions. Okay, these functions are actually polynomials of degree K-2. Then what we're going to do is, well, this is just a matrix of polynomials, but it's a matrix for every input. So what we're going to do is we're going to find a rank decomposition of it. Okay. What we show is that you can do this using a rational map if you have different inputs. Okay, so for every input you get a particular matrix which has a particular rank decomposition. We're going to find a rational map that does it essentially for all points, or for maybe all the points that make the matrix have a particular rank. This is just kind of a rational, or if you want, an explicit version of the adjoint matrix from linear algebra, or an explicit version of Kernel's rule, whatever you want to think of it, however you want to think of it. So that part is one thing, and it's basically a rational version of linear algebra stuff. So still no algebraic geometry here. So the algebraic geometry enters the picture in this step. So we are going to work with a particular variety. Particular irreducible variety, let's call it X for a second, calligraphic X. And restricted to that variety, so if only we're talking about inputs that come from this variety, we are going to take this matrix dt from before and take iterated derivatives of it, total derivatives of it. So again, each time we're talking about, instead of a matrix, a 3-dimensional array, 4-dimensional array, etc. And kind of this is the engine, what makes part one work, this lifting theorem. Okay, because the basis of this process, of this induction, is this rank decomposition for the initial matrix dt. But then we're going to use the lifting theorem to get a partition rank decomposition also for ddt, and then dt, etc. Once we do it k-1 times, then essentially, in some sense, we loop back to get t back. Again, why? Because t is just a polynomial map. So the degrees increase every time you apply total derivative. And so eventually we get not just a partition rank decomposition for a derivative of t, but also for t itself, with the annoying caveat that all of this happens in some variety. And so this would mean that the decomposition that we get has coefficients in the algebraic closure, which is not satisfactory, right? Because the entire question, right, partition rank is a notion that talks about decompositions in our ground field. So this is not enough, but it's something. So this is where part one ends, where we get a partition rank decomposition for any tensor, hopefully a partition rank, a smallish partition rank decomposition, but it's over the algebraic closure. In the second part of the proof, we're actually going to construct a particular variety X with an additional properties that would make the decomposition that we find, it would make sure that that decomposition actually has coefficients in the base field. Okay, and so those part one and part two combined would give you the partition rank decomposition over the base field for our tensor, and the challenge would be to show that the length of this decomposition is bounded by, the analytic rank times the constant. Okay, any general questions about the strategy?
Yeah, can I ask a question? So this strategy in part one, where you take a bunch of derivatives of these polynomials that could have degree something like k, if the characteristic of the field divides the degree of the polynomials you're taking the derivative of, then it seems like you're in a lot of trouble. Yeah. So is this like the core of where this restriction on the field size comes from, or the characteristic of the field?
So that's a great question. The answer is that we have absolutely no restriction on the characteristic. So our proof works for any characteristic. Why? Well, it's precisely because of what you said, except what you didn't take into consideration is that we're working with multilinear polynomials. So this entire issue that you just mentioned with the characteristic never happens. Okay? Just never happens. Okay. Any more questions? Okay. Okay, so if we're going to talk about, if we're going to move to the algebraic closure and talk about algebraic geometry, then we need a geometric version of, or a geometric analog of analytic rank, right? Analytic rank makes sense for finite fields. Now we're working over the algebraic closure. So we have this notion of geometric rank, the analog of it. So formally, you just look at the kernel variety. So what is the kernel variety? You take the map that corresponds to the tensor, and you look at all its zeros. Okay, so this is a variety, right? This is a certain variety cut out by polynomials of degree k-1. And like any variety, it has dimension, or in this case, it has some codimension. This is the geometric rank. Okay. So if k equals 2, then this T is a linear map. So we have a bunch of linear equations cutting out the variety. And so this variety is just a linear subspace. So it's a flat variety. And if it's a flat variety, then its codimension is just the usual notion of codimension from linear algebra, n minus the dimension from linear algebra. And so the geometric rank is just, right? It's the codimension of the kernel, which is just the rank of the matrix. So just like analytic rank and partition rank, for k equals 2, also the geometric rank agrees with the usual notion of rank. What happens for k greater than 2? Well, then we get, it's a different story. Then the kernel is no longer a linear subspace. It's some kind of complicated variety. And then, then it's the realm of algebraic geometry. And then we really need to talk about the notion of codimension from algebraic geometry. Okay. And by the way, the fact that this is very much related to analytic rank, I think is kind of evident, right? Because analytic rank looks at almost the same object. It looks at the solution set of all these, or the zero set of all of T, of the map T, except we're talking about solutions in the ground field in the definition of analytic rank, whereas here we're talking about solutions in the algebraic closure. If over the ground field, or the ground finite field, we can then, it's a finite number, the number of zeros, and then we can normalize it and you get analytic rank. Here you talk about the codimension of this variety. Okay. So here's a key definition. So we're not actually going to work directly with the geometric rank. That's kind of not subtle enough of a notion for us. So we're going to not work with the codimension of the kernel, but we're going to work with some new definition, which we call the codimension sub f, or the dimension sub f. So what is that definition? So here's the definition. It might seem a bit mysterious at this point. So it's the largest dimension of a subvariety. So you start with a variety V. We're talking about a subvariety Z that, even though it's a subvariety, it still contains all the F rational points of the original variety. So we want a variety, subvariety such as this, but we also want it to have these interesting properties. So we want Z to have a top dimensional irreducible component. Okay, so remember that every variety can be written as just a union of irreducible components. They can have all kinds of dimensions. We're talking about a component of the maximal dimension, of the largest dimension in Z. And this component also has to be not just an irreducible variety, but it has to be a variety, an F variety. It should be cut out by polynomials or with coefficients in the ground field. And we want there to be some quote unquote generic point on that component, which is F rational. Okay, and what do I mean by generic? It has to be non-singular in a strong way. So I'm not defining what strong is at the moment, but it's some kind of a generic condition. Okay.
Is it at all clear that such a thing exists? I mean, would that be part of your job to prove that this thing?
Well, I guess trivially it exists. You can always take
Wait, no, top dimensional is saying that it has a particular dimension, right?
No, it's top dimensional in Z. So Z has all bunch of points. Z has all kinds of components of different dimensions. Those with the highest dimensions of Z within Z. That makes sense?
Not yet.
Let me say something else. Like F is an algebraically closed field, then really this definition is not interesting at all. This is just the usual notion of dimension. Because if you just take an irreducible component of top dimension of your variety V, so you just take Z to be V, all of V, and you take any top dimensional irreducible component, any of the irreducible components that have the largest dimension in V, a generic point there is going to be, definitely it's going to be an F rational point because we said that F is algebraically closed, but it's also going to be strongly non-singular. And so for algebraically closed field, obviously this is well defined, and it's actually just equal to the usual notion of dimension. For general fields, we will have to work out to actually not just prove that, not just actually find such a variety, but also show that this variety Z, subvariety Z, has some additional nice properties. That is, in a sense, it's not too complicated. Okay, so that's a bit much for now, and later we will see why this definition, is even relevant to begin with. Okay, so let me just finish this slide. So for the rest of the talk, let's assume that T is a K-Tensor and our ground field is a perfect field. Basically, every field that you can think of is a perfect. Okay, so finite fields are perfect, algebraically closed fields are perfect, characteristic zero fields are perfect. So that's not much of a condition. So I mentioned that the proof has two parts. You can kind of summarize each part with an inequality. So the first part is just the inequality, the bound at the partition rank. It's an upper bound on the partition rank. It's bounded by a constant times this notion that we defined, the codimension sub f, so n minus the dimension sub f, of the kernel variety. Okay, so in the first part, we show that this definition that we just came up with, it upper bounds the partition rank. So we can find a partition rank decomposition whose length is not much more than this codimension sub f. And as I said, if f is algebraically closed, then the right-hand side is just the usual notion of codimension of the kernel, which is what we call the geometric rank. Part two is a lower bound. Now it's a matching lower bound. It's a lower bound on analytic rank. We're showing that this codimension sub f is sandwiched between partition rank and analytic rank, with some error term that if the field size is large enough relative to the analytic rank, this error term is negligible. And so this would finish the proof. This would sandwich this quantity between partition rank and analytic rank, and therefore prove that analytic rank is at least partition rank with this constant. Okay, any questions about this outline?
So can I say for the second part, so the analytic rank you can describe in terms of the number of zeros of this variety defined over F.
Yeah.
And so if I tell you the dimension and the degree of that variety, then you can use some version of like the Langevin bound or something like that. Is that what's going on in the the sort of like part 2 core idea?
Exactly. Yeah.
Okay. And the error term is like a little complicated because it depends on like geometric properties of this thing. Yeah.
Right. Exactly true. Except we'll need.
Okay.
So first of all, we'll need. I will talk about part 2 later, but we will need some some process in order to find this subvariety Z and to show that it actually satisfies all these properties. But also we will need to bound its degree, kind of its kind of complexity, its geometric complexity. The usual notion of that is called the degree of a variety. Turns out that this notion is actually not quite subtle enough for us, so we will need to adapt this notion to come up with a new definition of degree of complexity of a variety, and that one we could analyze, and if we do that, then we get this error term. Okay.
And this is like an end of the talk type question, but like, do you have examples to show, like in the remark, is that inequality sharp? I mean, do you have examples where the partition rank is that small? Like what can be improved here?
It might be that the constant, first of all, I suspect that if you kind of go over our proof and do things somewhat more carefully, you can maybe improve the constant here by a factor of 2, I think. But we don't have a lower bound on the constant here. So the constant can be much better. I don't know much about that. And what else can be improved? The fact that for the analytic rank question, how small can we get the finite field to be and still make our arguments work? Okay, cool. So let me move on. Let me give you kind of a general sense of the core thing that's going on in the upper bound. Don't have much time, so I'll try to go over this kind of quickly. So I won't talk about this slide. I'll just say that whenever you see the notation C superscript R of V, so V here is just a space of all tensors, or K-Tensors. This is just our notation for the set of all partition rank decompositions. Okay, so we want to be able to label them. So the set of all possible partition rank decompositions, we give it a name, CR. So CR specifically contains the partition rank decompositions of length R times this constant. Okay, but there isn't much there except just CR is our notation for the set of all partition rank decompositions of bounded complexity, of length of complexity R times something. Okay, and before I talk about the core step here, which is the lifting theorem, let me just mention one definition. So if you have rational maps F and G, and you have some subset calligraphic X, maybe a variety or something, then we say that F and G agree on the variety if they are equal for every point where both rational maps are defined. Okay, so a rational map might not be defined in some of the points of calligraphic X. For those points, I don't care about. But whenever the rational maps are both defined, I want there to be an equality between F and G. Okay, so here is the lifting, finally the lifting theorem. It's a bit of a mouthful, but let me just kind of scan the main objects here. So we have two inputs to this theorem. We have an irreducible variety X, an F variety, so cut out by polynomials over F, and some choice of a special point which is non-singular on that variety. The other object we have here is a polynomial tensor. So maybe F is just a polynomial. So this is formally it's a map from n variables to the space of all matrices. Okay, all n by n matrices or m by n matrices. It can also be, you know, 3-dimensional arrays, etc. So it's F is just, if you want to think about it, you can think about it as an array of polynomials. Okay, a 5-dimensional array where every entry is a polynomial. So this is F and this is X. And here is the condition and here is the guarantee. So let's parse the condition here. The condition just says that restricted to that variety X, F is a partition rank decomposition. So IP composed age, excuse the notation, I just skipped the previous slide, which might have made things more easy, but age just gives you a partition rank decomposition of length R times the constant. And once you apply this IP on it in a product, then that gives you back your tensor, right? The tensor that you get if you take all the components of the partition rank decomposition, multiply them in pairs and sum. Anyway, so bottom line, if you have the condition in the lifting theorem is if half F, this polynomial tensor, has a partition rank decomposition in every point of the variety X, and when I say every point, I mean with the exception of the points where this rational function h is not defined. If it's not defined, then it's not defined, and that's fine. We move to the next point. And this, and in particular, right? So this age, right? It gives every point in the variety. It gives a partition rank decomposition. I only assume that its domain, it's defined at x. That special point x naught. Okay, that's the only assumption that I want to make. If you have that, and it turns out that if you take the total derivative of the Jacobian of f, which is a tensor of one order up, then this too, right? It's still a function, right? It's still, every entry is still a polynomial. If you restrict it to that variety x, then we have again a partition rank decomposition. Okay, but now it's a partition rank decompositions of tensors of order a plus 1, but that's, you know, 1 plus. So it's a different, you know, object that we're dealing with, but we still have a partition rank decomposition. How big is the partition rank decomposition? Well, that's bounded by the original, so the length of the decomposition that was guaranteed for f, and the codimension of the variety. So this is where the geometry of the variety enters the game. That's a bit much. You can visualize this. So there are commutative diagrams at the bottom to visualize this. If you have your variety x, and for essentially every point in x, you have a partition rank decomposition given by age. Then if you take df, the total derivative of f, then we also have an h prime, another partition rank decomposition of that. Okay, we could stare at this for hours. It's pretty involved. I'll just very vaguely, very quickly mention that the general idea here is that you decompose for every point, or essentially every point in the variety, or most points, you decompose the entire space into the tangent space to the variety at that point and the complementary subspace. And you do this using a rational map. This goes again back to some rational version of linear algebra stuff. And then what you do is, right, you want to find a partition rank decomposition for df. So what you do, you look at its component in the direction of the tangent space and its component in the complementary direction. And the first one, we call this the main term. This one has a short decomposition simply because we rely on the assumption in the lifting theorem. Because f had a partition rank decomposition, then that means that df in that direction has a short partition rank decomposition. And what about the complementary direction? Well, we can't say much about it, but we're going to use the fact that it's a small subspace. So it's a subspace of dimension at most codimension of x. That goes back to the properties of the tangent space. And so we have kind of like a trivial decomposition for that component of df. Okay, so and you combine both of them carefully, and you can show that the new partition rank decomposition is, the length of it is what I wrote before, the maximum between R and the codimension of X times that constant, 2 to the K minus 1 minus 1. Okay, I think I'm out of time. Okay. So maybe I'll just quickly mention that using the Lifting Theorem, we basically finish the proof. So what we need to do is to look at a particular, or any point that is non-singular, but also achieves the maximal rank that DT ever achieves on that variety. That would make the basis of the induction of the first step for the lifting process work. Then we iterate it, like I mentioned before. And if you carefully check this, then eventually you get a partition rank decomposition. The point is that after you take K minus 1 iterations, you get a tensor, which is where the entries are not functions. So you can plug in whatever point that you want, and you're still going to get always the same thing. These are constant functions. But if you plug in a point x naught, which is an f rational point, then that guarantees that the entire partition rank decomposition that we iteratively construct has coefficients in the ground field F. Okay, and as we said earlier, this gives a partition rank decomposition of the originality, and the length of this decomposition is bounded by the codimension, and this quantity R that I defined, which is also bounded by the codimension. So, and the codimension is, so really what this means is that we work with the codimension sub F. So if you go over the steps here carefully, you will see that this is exactly the definition of the dimension that you need for the whole proof to work out. So not the usual codimension, but codimension sub F to make this entire thing work. So the crux of the matter is that we don't apply the iterative process on the kernel itself, but rather on this irreducible component that's given by this definition. So this is the first part, this bound on partition rank. The second part is a lower bound in the analytic rank by the same quantity. And this goes back to some kind of a somewhat subtle iterative process to find this variety Z, while also controlling how complicated how complicated this variety gets over the iterations. For that, we need some kind of a version of the usual notion of degree, but ultimately you can do the analysis properly. So yeah, there's some interesting math here, but if you do this properly, you get the lower bound analytic rank and you're done. Okay, I think I'll stop here.
Okay, thank you very much.
Thank you.
Any questions for Guy? Let's see.
I have a question going back to like the start of your talk.
Mm-hmm.
You said that generically that the tensor has rank close to n.
Yeah, both analytic rank and partition rank.
Right. Can you quantify that? What does that mean exactly?
Oh, I'm not sure, but I would bet that it should be like n times 1 minus little of 1, where the little of 1 goes to 0 with the size of the field, if we're talking about analytic rank. If you're talking about partition rank, I won't be surprised if the generic rank is literally n. I think people studied these questions, by the way. I think there are papers about this.
Yeah, I like over the real numbers, I know that if you have like a 2 by 2 by 2 tensor, then like 75% of the time it has rank 2 or something, but it's not like 100% of the time thing. Do you know what I mean?
Yeah, actually, yeah. But the issue is that you're talking about a different notion of rank. So you're talking about a notion of rank, which is a number between 0 and n squared.
Right.
And so there's a difference between the generic rank for 3 tensors. The generic rank is, I think, something like 1/3 n squared, but the maximal rank is actually something like 1/2, I think. I don't know, there's some gap between the maximal rank and the generic rank.
I see.
I don't think that's the case for partition rank.
Okay. Thanks.
I think I wanted to ask basically the same question in a different way, where like if you look at matrices over a finite field FQ, you have these n by n matrices, and you can count like exactly how many of them have a given rank. Like most of them have rank n, but you can count the proportion of them that have rank n-1, n-2, and so on. So if you fix Q and now you look at n by n, like 3 tensors over FQ, now there's still finitely many. And it seems like you should be able to say something for fixed n and Q, but now you have to choose a notion of rank. So for example, what about like geometric rank? Is it known how those are distributed? Like what proportion as, for in terms of n and q of these q to the n cubed tensors defined over FQ don't have rank tensor like geometric rank n defined over.
Yeah,
you know what I'm saying?
so just to clarify, you're talking about a finite field, but geometric rank, of course, looks at the codimension in algebraic closure.
Sure. Yeah. So it's some geometric thing about this variety happens to be defined over FQ, but like, you could ask about the codimension as a variety over FQ bar.
Yeah. So yeah, that's a great question. As far as I know, this was not studied, it's not very surprising because the notion geometric rank and the way it's defined and this comes from just a few years ago. Kind of as a tensor rank, as a notion of tensor rank. So I that's why I don't think someone studied it in that much depth. But definitely that's a question you can ask. Definitely.
Other questions? So Guy, I'm just sort of curious. There are various complexity questions in linear algebra, like trying to classify a pair of operators on a finite dimensional space. Is there any connection between that type of problem and these complexity questions here?
Okay, I might not be the right person to ask. I don't know. I'm not sure. I'm not sure. That's my answer to you. What else can I say about this? I mean, you're talking about something that's particular to partition rank and analytic rank, or is this?
No, not at all, not at all. But there's some kind of there are complexity questions in linear algebra. Actually, what brings it up is the fact that when I looked at your paper and at some of the references, and then in some of the references there are some ancient papers of Gelfand and Ponomarev on the problem of trying to classify a pair of operators on a finite dimensional vector space, which are extremely difficult. And I was just sort of curious whether there's created this chain that somehow got from a problem that I was interested in a long time ago to partition and analytic rank.
So okay, I don't know, but that could be an interesting avenue to explore if there's a connection between the two. Yeah.
And